Applications: profit, revenue, and cost. So, to apply some of the things we've learned about derivatives and maximums and minimums and inflection points to various parts of your life, we're going to start with a business model. We're going to talk about how this might apply to economics. In order to do that, we have to have some common language to start talking about our functions. So let's talk about the three types of functions we're going to be looking at. First is the cost equation. The cost equation is written C of Q, where Q represents quantity. Now, the cost function is going to represent the amount of money it takes from the seller's perspective to make a product. So imagine that you're going to sell ceramic llamas. So the amount of money it takes you to make these llamas before you've sold them is your cost. Now, fixed cost is your cost before you've actually made any of these ceramic llamas. So these are your upfront costs. So maybe you buy the mold. Maybe you buy a building where you're going to produce these. Before you've actually made any of the product, you have these fixed costs. And again, that's the cost when you've made zero of your item. The next equation that we need to look at is revenue. So revenue is the amount of money that you take in from selling your product. The way that we calculate revenue is the price that you're selling your product for times quantity. So let's say you sell your ceramic llamas for $10 each. If you sell 5 of them, your revenue would be $50. So price times quantity. What's important here is that we remember that price is a constant and Q is your variable. Finally, we talk about profit. So profit we write as pi of Q. And profit is the amount of money you make by producing and selling an item. So your profit is your revenue minus your cost. So the amount of money you take in minus the amount of money that you spent. We're really hoping that profit is positive. However, as some business models will show you, sometimes you can have negative profit as well. So in relation to what we've been doing, there's some special terminology that we use when we talk about the derivatives of these functions. And when we talk about profit and revenue and cost, and we talk about the derivative, we're going to use the word marginal. So marginal in economics means that you're looking at the rate of change of the function. So when you talk about marginal cost, that's the derivative of cost. Marginal revenue is the derivative of revenue, and marginal profit is the derivative of profit. So now that we understand what these equations represent and the terminology, let's look at some ways that we can apply what we've learned in the earlier sections to figure out some interesting things about these functions. Example 1. Suppose the cost to produce an item is given by C of Q equals 10Q squared plus 1400, and the revenue is given by R of Q equals 4400Q. Now, there's a series of questions here that are going to represent all sorts of different things we can find out about these functions and about this particular model. So we're going to go through one by one, but I want to point out that it's the last 3 that really get into the derivatives and the things we've been applying them to so far in this section. So part A, how much does it cost to make 15 items? So that means we want to know what it's going to cost us to produce 15 of whatever it is that we're making. So that means that we're plugging 15 into our cost function. So wherever we see a Q, we're substituting in a 15. And then we're going to crunch all of these numbers together, and we get that it's going to cost us $3,650. So when we talk about cost and revenue and profit, we're always talking about money. So we're always going to talk about this in terms of dollars. So $3,650 is how much it costs us to produce 15 items. Part B, how much does each item cost when they are for sale? Now, the wording of this question is a little deceiving. You see the word cost here, but we're not talking about the cost function. When we ask how much does it cost when they are for sale, we're really looking for the price here. What is the price that we are selling this item for? Well, remember that price shows up as part of the revenue equation. Revenue is price times quantity. So taking a peek at our revenue equation here, we have 4,400Q. So knowing that revenue is price times quantity, that means that my price here is $4,400. So whatever this item is that I'm making and selling, I'm selling it for $4,400. Part C. What is the profit function for this model? So remember, profit is going to be revenue minus cost. So that means here, I'm going to take my revenue equation minus my cost equation. Now, my revenue equation only has one term, 4,400Q. It's all one term, the two things multiplied together. However, my cost function has more than one term. So when I subtract it off, I'm going to use parentheses to make sure that my minus sign is distributed properly. So my revenue was 4,400Q minus cost, which is 10Q squared plus 1,400, and that gives me my profit function. Part D wants to know, what is the quantity that maximizes profit? So now we're into the part where we have to remember what it means to find a maximum. We know from before that maximums are going to happen at critical points or endpoints. We don't have an interval restriction here, so we're really looking for our critical points to try to determine if that's where we'll have our maximum. So if we want to maximize profit, we want to take the derivative of profit and find the critical point by setting it equal to 0. So here, when I take the derivative of profit, that's called marginal profit, I'm going to get 4,400 minus 20Q. Now, I want to know, when does that equal 0? So if I bring the 20Q over to the other side, and I divide both sides by 20, I get Q equals 220. So I have a critical point when my quantity is 220. But I want to be sure that I'm maximizing profit. If I accidentally minimize profit, that really wouldn't be good for business. So here, what I can do is if I check the second derivative of my profit function real quick, I notice that the 4,400 is a constant, so that goes to 0. And then the second term, I end up with minus 20. So I find that my second derivative is negative. If my second derivative is negative, that means that the entire original function is concave down, which means that my critical point has to be a maximum. So I'm in luck here. Q equals 220 has to be the maximum of this function. So that's the quantity that maximizes profit. Part E wants to know, what is the maximum profit that can be achieved? So now that I know when this maximum happens, Q equals 220, I want to know what the actual profit is. So I need to take that 220 and I need to plug it back in to the profit function, which is what we found in part C. So everywhere that there's a Q, I'm going to plug in a 220. And again, I'm being careful with the second part of the term, and I'm using my parentheses because that minus sign has to go to everything in the cost function. And when I plug this all in carefully, I get 482,600. And remember, all of these functions, cost, revenue, and profit, are all talking about money. So again, $482,600 is the maximum profit that can be achieved. So again, if I'm looking for the maximum of a function, even if it's a function I'm not really familiar with, I can use whatever function I have and use derivatives to find critical points, which are going to identify where maximums and minimums exist. Let's look at another. Example 2. Let's see if Q represent the cost, R of Q represent the revenue, and pi of Q represent the profit of a product with quantity Q. Part A. When profit is maximized, what is the relationship between the derivative of cost and the derivative of revenue? So let's review what we know about the profit function. Really, we don't know too much, but we do know that profit is revenue minus cost. Now, with revenue minus cost, we don't have the derivatives in there yet. And so we're trying to think about what this has to do with the question being asked. So the other important part of this problem is the part of the question that asks when the profit is maximized. So remember, when we want to look for a maximum, we're interested in where the first derivative equals 0. We know that if we have a maximum, that the first derivative of profit will equal 0. Well, what do we know about the first derivative of profit? So here, marginal profit, we have two terms, revenue and cost, that are separated by subtraction. When we take derivatives, if things are separated by addition or subtraction, we can take the derivative term by term, which means we can write the derivative of revenue as R prime of Q, or marginal revenue. And then we can write the cost derivative as C prime of Q. Now, if we're at a maximum, that means we're at a critical point. So the difference between these two things will have to be 0. Well, that tells me something really important, because if I were to add C prime of Q over to the right, I will find that R prime of Q equals C prime of Q. So that tells me that when profit is maximized, the marginal revenue has to be equal to the marginal cost. This is a little tidbit that comes in handy in strange ways, but it's something that's useful in a lot of ways. If our marginal revenue equals our marginal cost, we have the right condition for the profit to be maximized. Part B. If the marginal revenue of cost at 45 items is $57 per item, and the marginal revenue at 45 items is $62 per item, approximately how much additional profit is earned by the 46th item? Now, we have to be a little careful here, and our analysis is the 1 unit marginal analysis that we were doing when we were talking about derivatives before. So I want you to notice that the information we have is about what's happening when Q equals 45. So if we're talking about the additional profit earned by the 46th item, then we're looking for the amount of profit that we get from moving from 45 to 46 items. Remember, when we talk about derivatives, we're talking about increasing the independent variable by 1 unit and looking at what the change is in the dependent variable. Here, that dependent variable is profit. So we're looking at what happens as we move from 45 items to 46 items. And so again, the additional profit is the marginal profit. So that's the rate at which the profit is changing. So we want to talk about marginal profit at 45 items, because that's going to tell me how much additional profit I make to go from 45 to 46, and therefore identifies the additional profit earned by the 46th item. Well, as we saw in the previous part of this example, we know that marginal profit is marginal revenue minus marginal cost. But we're looking at all of these things for Q equals 45. So we need the marginal revenue at 45 minus the marginal cost at 45. So we know these values from the earlier part of the problem. It's going to be $62 per item minus $57 per item, which tells me that the marginal profit is $5 per item. So that tells me that if I were to go from making and selling 45 items to making and selling 46 items, I will receive an additional $5 in profit. Let's look at one more example. Example 3. A theater has 1,000 seats, and when they set their ticket price at $10 per ticket, the theater sells out, so they sell all 1,000 tickets. For each additional dollar charged, the number of seats purchased is reduced by 50. Part A. Find the linear equation that fits this data. Instead of using the variables x and y, substitute Q and P into your equation. This is what we call the demand equation. The demand equation relates how many tickets will be demanded depending on the price that you're picking. So we want to have a relationship with Q and P. So it doesn't matter which way we set this up, as long as we're careful and we're consistent. So how do we do this? So we want to write these informational points, 1,000 seats, $10, as points as though we were plotting them on a graph. So the first point would be 1,010. Now, the second point that we have from information from this problem here is that if we charge an additional $1, so that means instead of 10, we're going to have 11, the number of seats purchased is reduced by 50. So we're going to subtract 50 from 1,000, and that'll give me 950. So these are two data points. And normally, I write my points x comma y. But I want you to notice here that what I'm talking about is quantity comma price. So what I'm going to do is I'm going to come up with a linear equation that fits this data using y equals mx plus b. Once I have the equation of that line, I'm going to change my x and my y into q and p so that I have a demand equation. So let's find the slope that's going to fit between these lines. So remember, slope is change in y over change in x. So here, I'm going to do 11 minus 10 divided by 950 minus 1,000. That's going to give me negative 1 over 50. So the slope of my line is negative 1/50th. So here, I have y equals negative 1/50th x plus b. In order to solve for b, I need to plug in one of my points. It doesn't matter which point I plug in, I'll get the same answer. So I'm going to use the first one. So for my first one, if I plug in my point, I have 10 equals negative 1/50th times 1,000 plus b. Negative 1/50th times 1,000 gives me negative 20. If I add that over to the left, I get b equals 30. Which means the equation of my line is y equals negative 1/50th x plus 30. Now remember, we don't want our answer in x's and y's. We want it in q's and p's. So we go back to our original setup, and again, we had q comma p, quantity comma price, which means that instead of x, I'm going to write q, and instead of y, I'm going to write p. So I have p equals negative 150q plus 30. So this is my demand equation. And again, a demand equation relates price and quantity. So you, as the producer, can figure out the right balance. We could solve for Q if we wanted to and then vary the price, or we, in this case, are varying Q and using that to set the price. Now, remember from before that revenue is price times quantity. Part B. Using your equation from part A, set up the revenue equation by substituting the demand equation in for P. So what does that mean? So remember, revenue is price times quantity. What this is saying is that instead of P, we're going to use what we just found for P setting up our demand equation. So that's going to give me negative 1/50th Q plus 30 times Q. Now I can distribute that Q through and simplify a little. So I'll get negative 1/50th Q squared plus 30Q. So that's my revenue equation for this particular model. And again, I got this set up by plugging my demand equation in for P and then distributing the Q. So now for part C, I want to find the price and quantity that will maximize revenue. Well, all the work I was doing before was to get my revenue equation set up. Now that my revenue equation is all set up, I can maximize it by using derivatives. So again, I want to find where the first derivative of this function equals 0, because then I will have a critical point, and I know that maximums happen at critical points. So let's see what the first derivative looks like. So here, the first derivative of revenue, we go to the first term. I have negative 1/50th Q squared, so the 2 comes down. I have negative 2/50ths Q to the 1 power, plus the derivative of 30Q is 30. And I want to know, when does that equal 0? So now I can take my Q term and bring it over to the right, and I will get 30 equals 2/50ths Q Now I'm going to multiply by the reciprocal of that fraction to get it out of there. So multiplying both sides by 50 over 2 is going to give me that Q equals 750. So now I have my critical point. If I were to take the second derivative of this function, I would have negative 2/50, which tells me that my revenue equation is concave down everywhere. Since it's concave down everywhere, I know that my Q has to be a maximum. So that's the quantity that maximizes my revenue here. I also want to know the price. So in order to find the corresponding price, I have to go back to my demand equation, which is way up here in part A, and I need to substitute my Q in. So I have negative 1/50th times 750 plus 30. If I crunch that number, I'm going to get P equals 15. So price is going to be in dollars. So I could figure out what my revenue would be here by multiplying P times Q, but that's not what the question asked. So I'm able to find all sorts of things if I carefully set up my equations and use the calculus that I've learned to evaluate them.